When we think of our solar system, we have this mental image of everything going around the sun in nice and neat order, perfect circles. Everything is really hunky-dory on that. Actually, nothing could be further from the truth. We discovered last week that the orbits of the planets are not circular. They are actually ellipticals, which means that there are times when we are closer to the sun than at other times. When we are closer to the sun, we move a little faster in our orbit. But not only that, but our solar system is not stagnant. It's not static in space. The sun, dragging all the planets, actually move through space. And the gravity of the sun just drags all the planets along. Now you might be wondering, where is it going? And it happens to be a part of our galaxy. We are on the Orion Spur. Let's see if I can get it going here. Oh well. And as our galaxy turns, it drags our solar system with it. Our solar system makes one trip around the center of our galaxy every 250 million years. Those are Earth years. By the way, everything we know, talks about Earth years. But in order to figure out how our planets started, how our solar system started, we need to go back in time, approximately, about 5.5 billion Earth years. At that point, the second star that formed on the Orion Spur is about to undergo its demise. The heavier elements are gathering in there, and it's about ready to change the heaviest elements into iron. And when it does that, we have a supernova. At this point, the elements that are beyond that of iron, in other words, element 26 and above, are now changing into heavier elements. And as a result of this is where we get our gold and other elements that are beyond element 26. So we have our expanding gas cloud, and soon in the middle of this gas cloud, we will have the cloud of heavier materials slowly condense into a much tighter cloud that will give birth to our solar system. So the temperatures are rising inside that cloud and eventually will form a new star. And this is our sun. Our sun actually started, our proto-sun actually started as a yellow star, and as it ages, it actually gets hotter. Our star was about 10 to 15% cooler when our solar system started. So as we get older, our star gets hotter. So here we have our solar system, and we're wondering, how in the world did it actually start? What forces caused the creation of our planets? And it's really an amazing phenomenon. If you have basically two asteroids, and they have similar composition, they could actually weld each other together. Here we have Thule Ultima, which is the last asteroid that was examined by New Horizons spacecraft. It is beyond the orbit of Pluto, and as you can see, it's only 21 miles wide. And it appears to be made of two different pieces, and it is. These two asteroids actually came together, and because it was in the vacuum of space, the materials didn't have some kind of oxidation layer surrounding the material. As a result, we actually had literally iron touching iron. And according to a physicist named Feynman, the atoms didn't know that that was the end of the rock. They were kind of confused. And when the two rocks met, they actually absorbed each other. They actually welded each other to themselves. And that process looks something like this. The two same materials will actually weld to each other in a vacuum. So as a result, we have these asteroids out in space. It's the material from the explosion of that supernova. And as they're flying around, they will eventually meet each other. And then the inertia will actually cause them to begin to spin. As you can see, this particular asteroid is made up of many different pieces that all came together at some point and formed this one very odd looking, this looks like a snowman. Anyway, but this asteroid does spin because of inertia. And as a result, if you turn it on its side, you can see it's actually somewhat flattened. That just happens to be how it is. So what we have is our way out in our asteroid belts, or actually in our newly forming solar system. We have lots and lots of rocks just floating around, and if they happen to touch each other, they will fuse to each other. The inertia will cause them to spin, and this asteroid, this newly formed asteroid, will actually travel through the dust and dirt that makes up our new solar system, and it gathers all this dust and dirt, forming a larger and larger asteroid. As it forms a larger and larger asteroid, then the internal forces of collapsing gravity will cause that asteroid to heat. At this point, it's gathering more and more dust, and as it does, the temperature will go up, and it will eventually form a giant ball of glowing goo that's encased in a dust cloud. This dust cloud will eventually condense into a spinning disk, and from this spinning disk, with a new planet will form. Now, depending upon how much material it happens to pick up, it will determine the size and the composition of that particular planet. If you take a look at our solar system at this point, it is absolutely inundated with lots and lots of rocks. The heavier rocks will combine with others to form clouds of dust and dirt that will eventually condense into planets. Now, remember we talked about our bathtub ring, and just like a bathtub, the heavier materials will fall toward the middle of the solar system, while the lighter materials will form, well, I guess you can call it the bathtub ring. So as gravity causes the materials to condense, the heavier materials will fall toward the middle, and the bathtub ring will form on the edges. As a result of that, the heavier the rocky planets will be closer to the sun, while the gas giant planets are much further away. Usually, there is something called a frost line, which divides that point. So the frost line basically uh, is the border between rocky elements and gaseous planets. What's interesting about all this, because of the spin of the disk that where all these form from, all these planets are moving in the same direction. They orbit around the star in that same direction. In fact, they will even have their own spin, their own rotation in the same direction. As you can see, they are all moving clockwise as you look down from the North Poles, from the shall we say, the upside of these planets. Now, this is not the way things are now. In fact, if you take a look at these two planets, that happens to be Venus and the planet Uranus. If we want to take a look at what they are doing right now, what we find is the fact that they are not going in the same direction. As you can see, Venus is actually moving backwards, and Uranus is rotating on its side. So, and they are certainly not going at the same speed. One of the things that determines how fast the planet rotates is the amount of mass, or the inertial spin, of these planets. And if we take a look at, and if we compare all of these planets together, we find that they are going at different speeds. Jupiter is spinning the fastest, and Venus is, well, it's spinning backwards, but it's still spinning at more than 240 some odd days for one complete rotation. So that's an awfully slow spin. We can take a better look at it with this. You can see that Mercury is barely spinning. It spins once on its axis in 58 days. Venus spins once on its axis every 243 days. What's interesting is the fact that its day is actually longer than its year, which would give the calendar makers a real migraine. Earth spins once every day, and Mars spins every little bit more than a day. So each of them are moving at different speeds, and this would have to do with the mass of each of those planets, and sometimes something may have happened in times past that would have changed the original spin and the original orbit of that planet. Now, an eventual question, and I've gotten this, I don't know how many times, what would happen if the Earth were to suddenly stop spinning? And I actually have a very distinguished astronomer answering that. If you stopped the Earth and you weren't seat belted in, you'd fly about 800 miles an hour. So you got that? If the Earth suddenly stopped spinning, it would not be a good day. I mean, at the best, it would cause the sun to actually hold still in the sky, which brings up a Bible story, so I'm not quite sure where to go on that. Anyway, but if you take a look at our solar system, or at least our inner solar system, you can see that we have terrestrial planets and gas giants. So we have rocky planets and gas planets, and they are separated by belts of asteroids. The Kuiper belt is nothing but another belt of asteroids. And as a result of this, we find once again that the terrestrial planets, Mercury, Venus, Earth, and Mars, are rocky. They're generally smaller. They are more closely spaced, and they are closer to the sun. The gaseous giants, Jupiter, Saturn, Uranus, and Neptune, they have more helium and hydrogen. They're less dense. In fact, if you had a bathtub big enough, you would find that Saturn would float. Now, I'm not sure if you squeezed Saturn, if it would make a ducky noise, but that would be a good way to tell what Saturn is made out of. Anyway, but the gas giants are called giants because they are larger. They are spaced further apart, and of course, they are further from the sun. So if we were to take a look at a planet that was just forming, keep in mind that these asteroids that picked up more and more material would be more massive, their gravities would increase, and they would be collecting more and more rocks. They would be hit a great deal. But looking at our inner planets and our outer planets, we would find that everything is actually inside of the Oort cloud, which is somewhere in the vicinity of could be as much as 100,000 astronomical units wide. Now, how big is an astronomical unit? One astronomical unit is about 93 million miles. As you can see, there's about 63,000 astronomical units in a light year. So the Oort cloud would actually be, or could be, larger than a light year. If you were to put our Oort cloud, the sun's Oort cloud, next to the closest star system, which would be Alpha Centauri, the distance between the edge of each of the Oort clouds would be about 2 light years, which is hardly a distance at all. Anyway, but at the time that our planet formed, it was actually getting hit all the time. This is called the heavy bombardment, and it was about 4.5 billion years ago. And as time went on, as you can see, the colors of the hits are changing, and as we get more and more recent, you can see that there's actually less of them hitting the Earth. And as they hit the Earth, they will be melted into its component elements. The heavier elements, like iron and silicon and that stuff, would be pulled toward the center of the planet. So as a result, even though the initial Earth had a, shall we say, a carboniferous chondrite meteor, which means it's a rocky type of core, eventually, as the Earth melts, gases would rise to the surface, the iron would sink to the center, and the Earth would eventually gain a metal iron core with a rocky surface. So we could actually, at this point, jump from planet to planet and see how time has affected each of the planets. So we're going to start with the Earth because we happen to be on it. At least most of us are. So we have our Earth. It's spinning merrily once every 24 hours. But this picture of the Earth is actually incorrect. Our Earth actually is tilted about 23 degrees, 23 and a half degrees. And the question remains, why or what caused it to be tilted? And there are lots of different answers. The most accepted answer at this particular point is because at some time in its past, it was hit by something. This is the most disturbing picture. I mean, really, did it have to be red? Well, anyway, a lot of scientists feel that this is how our moon came to pass. The Earth, about, maybe about half a billion years or after it was formed, was actually hit with a glancing blow. And as a result, the spatter of rock and materials formed a moon right there. Watch that again. And probably one of the most realistic pictures of this, an artist by the name of Chesley Bonestell happened to be there. And he drew this picture of the early Earth. And you can see that our moon is a large semi-luminous disk, covers about half the sky. And the reason for that is because at the time that Dr. Bonestell drew this picture, the moon was only 10,000 miles away from the Earth. Now, right now, our moon is about 250,000 miles away, 250,000 miles away. So how in the world did it get so far away? Also, at this particular point, our moon went around the Earth about, something along the lines of about once every 18 days, rather than once every 29 days. So not only was it closer then, but it also orbited the Earth an awful lot faster. So what happened? Well, actually what happened is the fact that as the moon goes around the Earth, it takes a little bit of energy from the Earth. And it takes that energy and actually forces the moon into a slightly higher orbit. In the process of taking that energy, the spin of the Earth actually slows down. So we have the moon getting further and the Earth's rotation slowing. Now, right now, as it happens to be right now, the moon takes about 29 days to go once around the Earth, 27 and a half days actually. And it's sitting about 250,000 miles away. So the moon has gotten further away, and it's going around the Earth a little bit slower, and the Earth's rotation has slowed. Actually, it's slowed from about 18 hours from one rotation to about just under 24 hours per rotation. At some time in the future, is the moon going to escape from the Earth? The answer to that is no. It will, however, become locked in its position with one side facing the Earth at all times. The moon will actually stop spinning. Right now it spins once per rotation, and at some time in the future, it'll be locked in that position. And the Earth will no longer spin as well. It'll be locked in its rotation with the moon. That happens somewhere in the vicinity of about 43 days. So a day on the Earth in about 2 or 3 billion years will be the same time as the rotation of the moon. Is that something to worry about? Not really, because at the same time that's happening, our sun will actually expand in its size, probably engulf the inner planets, and to make matters even worse, the Andromeda Galaxy will probably collide with our galaxy, driving our Earth to drive our Earth away from its sun, and that's going to be a bad day as well. So I really wouldn't worry about the moon locking its position and the Earth's day lasting about 43 days at that point. Well, if we took a knife and cut into our planets, what we would find is the fact that the cores, the insides of these planets are a little bit different. The Earth has a fairly solid inner core and a liquid outer core. Most of the other planets will have a core, but it won't consist of a solid material. The crust, at least the Earth's crust, is made up of iron. Actually, a third of the crust is made up of iron. Another third is made up of oxygen. And the rest of the crust is made up of magnesium, sulfur, nickel, and trace elements. The mantles are made of mostly silicate rocks, like magnesium and iron, and the intense heat causes the rocks to actually churn. They will actually cool as they move toward the crust, and then they will heat again. So it will actually cause a churning action. It's this churning action that will actually form the magnetic field around the Earth. The core is spinning, and as it does that, and the churning action of the mantle causes our planet to produce a magnetic field. Because the core is moving on its own within the center of our planet, our magnetic field actually changes over time. In fact, given enough time, the magnetic field will actually reverse itself. And scientists feel that this is going to happen fairly soon. What is soon? Probably in the next 50 to 100,000 years. So I guess for one of us, that puts it in the same category as, meeting with the Andromeda Galaxy, but that's whatever. But as a result of this churning mantle, we have something that is rather interesting. We have something called plate tectonics, or the continental drift. And what happens is that the continents are actually floating on this mantle. And as they churn, the crust will actually move. The crust will, if they're moving toward each other, the side of the mantle will actually subduct, or will actually go under the other mantle. At other points, the crust will actually separate, and new crusts will form to fill up the spaces. Where one crust subducts under the other one, we could have volcanoes. Where the crust is formed, we can have heat vents and other volcanic materials. If two parts are actually pushing against each other, tensions will increase until finally there is a sudden release, and we'll have an earthquake. The earthquake could result in the ground not only shaking, but parts of the ground being uplifted. And if it happens on or near an ocean, it could form tsunamis. So this is something that, while other planets do show earthquakes or moonquakes or Marsquakes, it doesn't quite happen the same way on the Earth. On the Earth, we will actually have continents or plates that will move. And as you can see, if you take a look in the Atlantic Ocean, you can see that we have the Caribbean plate, and it's actually moving away from the African plate, and we have new land, a new ocean bottom being formed there. Meanwhile, over on the Filipino plate, on the side of the Pacific Ocean, moving basically toward the Eurasian plate, that's actually the space between them is actually getting smaller. One plate is subducting under the other one. So the effect of all this is the fact that Eurasia, China, Japan, are actually moving closer to North America. Meanwhile, North America, Africa, and Europe are actually moving away from each other. So, given time from the beginning of the plate tectonics, right after the Earth was formed and the materials actually came together to form plates, we actually have these plates moving around to the present. We'll let that go again. And those numbers are actually counting down in terms of millions of years. So it looks like a giant jigsaw puzzle. Now, because of this churning inside the Earth, it has actually made a magnetic field around the Earth. And this magnetic field is vitally important to life on the Earth, because it's this magnetic field that actually protects the Earth from emissions or from radiation emissions from the sun. The sun actually emits a solar wind, which is moving probably close to 700,000 to 1,000,000 miles per hour. And as these charged particles hit the magnetic field of the Earth, they will actually disperse around the Earth. If they do come back toward the Earth, they will form the auroras. Now, what about the other planets? Do the other planets have this type of protection? And the answer to that is some do, some don't. If we take a look at possibly the planet that we'd like to have this protection, like Mars, we find that Mars is very similar to the Earth in one sense. It does rotate similar to the Earth. It is tilted similar to the Earth. And at one point in its ancient history, it was thought that Mars did have a magnetic field very similar to the Earth. But something happened, and the topographical maps of Mars seem to indicate what may have happened to Mars. If you take a look, these are actually altitude maps, and as you can see on the left side, there's a lot of red region, which means that it's pretty high up. And if you take a look on the right map, you can see that there is a hole. There seems to be a depression on the lower side of the planet. And it is felt that at some time in the past, perhaps a couple of 100 million years after Mars formed, it was unfortunate enough to get hit by something pretty big. Something that was, well, it was enough to cause a great deal of damage. So Mars was hit by an asteroid that was probably about, maybe a third the size of the planet. And this asteroid actually caused energy to go through the planet. It actually caused the core of that planet to stop spinning. And the energy continued onward to the edge of the planet, to the surface of the planet, where on the side opposite the crater, we have the valley that at some point was molten, and the planet itself lost its ability to make a magnetic field, which resulted in the death of that planet. So when we get hit by radiation from the sun, it'll actually curve around us, and whatever happens to hit us will form the auroras at the poles. Mars, on the other hand, is pretty meager. Doesn't have anything that could possibly protect it. As a result, Mars' thin atmosphere will allow the sun's harmful radiation to reach the surface. As a result of that, according to the last probes sent to Mars called MAVEN, we find that the solar wind hitting Mars at close to 1 million miles an hour will actually strip away gases at the rate of about 1/4 of a pound per second. So this constant barrage of charged particles has resulted in Mars becoming probably a dead world. Now, that doesn't mean that it's totally dead. Probably wherever there's some type of protection, There might be some type of life deep within the soil of Mars, but at this point, nothing has been found. They have found evidence of organic chemicals within the surface of Mars, but nothing that at some point in the past, it's all been stripped away. However, without continental drift, Mars has something else. Well, watched Mars become a dead world, but Mars does have something called Olympus Mons. Olympus Mons could be the tallest volcano in our solar system. It's absolutely huge. We don't have anything even close to it on the Earth. Mauna Kea, our tallest volcano, keeping in mind that most of it's underwater. It's taller than Mount Everest, so it's absolutely huge. It's twice the size. How in the world did this happen? How does Mars, little Mars, about a third the size of the Earth, how is it able to manufacture a volcano twice the size of the tallest mountain on Earth? And the answer to that is actually quite simple. The Earth has continental drift. As a result, the plates will actually move over rivers and pools of magma. In Mars, on the other hand, does not have continental drift. As a result, any volcano will have a chance to constantly build on itself. As a result, it gets taller and taller. The next planet we want to look at is Venus. Venus, again, it has been called the Earth's twin in times past. However, one thing that has singled Venus out from us is the fact that up until about the last 20 years, the surface of Venus has been hidden by fairly thick clouds. As a result, if you look in some old astronomy books, they will never give you the rotation period of Venus simply because they didn't know it. There was no way of ever seeing the surface. However, with the invention of, shall we say, interplanetary radar and others, the surface of Venus made itself visible. And we have a very distorted, very, well, it's a real messed up surface. And the surface is changing. The surface on Mars is a fairly old surface. It's several billions of years old. It's been estimated that with all the things that are happening on Venus, the surface of Venus is only several millions of years old. But it has an unbelievably thick atmosphere. The atmosphere on Venus is more than 90 times the thickness of our atmosphere. It's made up of carbon dioxide. It has acid rain to the point where it virtually destroys any space probe that we've sent to it. The longest a space probe has lasted on Venus is a little bit less than an hour until the heat, the pressure, and the acid atmosphere eats it away. So Venus is not really a very nice place to visit. Temperatures on Venus easily top 800 degrees Fahrenheit. So even though it's not the closest planet to the sun, it is the hottest. Also, it seems to be rotating backwards. Now, there might be two reasons for this. One reason could be the fact that at some point in its early history, Venus was hit by some asteroid that actually knocked it over. The other reason I'll get into in just a minute, but if you take a look at the surface of Venus, you can see that it has these interesting shield volcanoes. Now, a shield volcano are actually volcanoes that come from the same lava pool, but the crust is moving. So it's a similar process of what happens on the Earth. So does this mean that Venus has plate tectonics like the Earth? Actually, it doesn't. The crust is changing, but it's not forming new crust, and it's not necessarily destroying the old crust. Here on the Earth, we have convecting, we have our subduction and the creation of new crust. On Venus, the crust, we actually have compression and the pileup of the crust material actually causing mountains. And then we have extension volcanoes over upwelling. I mean, the crust moves, but it's not the same as plate tectonics. As a result, Venus does not have a magnetic field that is protecting its surface. The energy from the sun actually heats the atmosphere to the point where we have basically we have actually uncontrolled solar heating that causes the planet to get hotter and hotter. So the planet is not protected by any means by any kind of magnetic field. The bow shock of the solar wind is virtually on the planet's surface. And as a result, Venus, it's not really a very nice place to visit. The other way that Venus could have slowed down was the fact that the solar wind reacting with the extremely dense atmosphere may have actually caused the planet, at least the drag of the atmosphere may have actually slowed the planet down. So given time, the rotation of the planet may have actually been slowed by the fact that Venus does not have a magnetic field. And at this point, it's actually slowed down to the point where it is now moving, actually going the other way. If we notice that Venus's rotation is increasing, then we know that our theory, at least those theories, could be correct. But it'll take years of watching before we discover why Venus is going the other way. Okay, looking at our rotation charts again, once again we find that the Uranus is rotating on its side, and which kind of makes for an interesting seasons on Uranus. Uranus revolves about the sun. I believe it's about every 160 years, 150 years, and half that time is one season, and the other half is another season. So it's you'll have part of the season with the sun in the sky. Of course, the sun would be quite dim, and then another season with the sun just nowhere to be seen. Not a very nice place to live. But how did Uranus end up like this? And when the Voyager passed Uranus and Neptune, it kind of gave us an idea. And one of those ideas is this one. Sometime in the distant past, an asteroid actually hit Uranus. And we know that something pretty major happened because it actually moved the axis of rotation, plus it moved the direction that the magnetic field is pointing to. So something hit Uranus so hard, it actually displaced the core of that planet. If you take a look down at the lower right, you can see that our magnetic field is nicely centered over the North and South Pole. If you take a look at Uranus, you can see that its magnetic field is not by any means centered over its North and South Pole, and in fact, it's actually displaced by a good margin. And one of the things that the Voyager happened to see at that particular point was the fact that the planet is actually rotating on its side, and in fact, the moons of that planet are actually rotating at the same plane as the disk, which seems to imply that the disruption of Uranus happened at a point where the planet was already formed and already had moons going around it. So it happened probably not too long ago, probably a billion or 2 years ago. But we do know that taking a look at the magnetic field of Uranus, it is somewhat lopsided. One side is definitely larger than the other. And this is what Voyager showed when it passed by. Voyager also took a look at Neptune and found that Neptune's axis of rotation, its magnetic nodes, north and south, are displaced even more than Uranus. So as you can see, the way on the right, that Uranus is actually displaced more than half the diameter of the planet, and the strength of that magnetic field is about half that, about a third that of the Earth. So it's certainly not a very, very strong field. If we take a look at the magnetic fields of the gas giants, we find that Jupiter, by any reckoning, is the magnetic field. It looks like it's about 3 or 4 times the diameter of our sun. So it is absolutely huge. Meanwhile, Neptune is rather small, and if you compare it, let's say again to the Earth, it would be about the same. So with all this spinning, does the spinning actually do something? Does the spinning of a planet have any effect on the planet, other than the fact that we have day and night? Well, actually, I'm going to kind of sneak into a little bit here. The spinning of the planet, which at this point we know is actually slowing down, given a couple of billion years, actually causes something known as the Coriolis Effect. And while the Coriolis Effect affects winds and affects ocean currents, here in the northern hemisphere, moving things are deflected to the right, which is opposite of what happens in the southern hemisphere. We have clockwise flow around high pressure systems. If ever you want to learn about weather, you have to learn the Coriolis Effect. And that's very, very easy to show, because all you have to do is be on something that is spinning around. If you are on something that's spinning around and you throw something, you have to actually adjust for that. You have to throw the ball where the person is going to be. If you're shooting something on a spinning platform, then you have to adjust for that. As you can see, the outline of that ballistic sphere, while it looks like it's going straight, if you are on that rotating base, you'll notice that it seems to take a curved path. If the Earth was static, if the Earth was standing still, there would still be a large pressure cell that would be in our atmosphere. It's called a Hadley cell. And there would be basically one giant cell in the northern hemisphere and one giant cell in the southern hemisphere. The air would be heated at the equator because it would have the direct effect of the sun. It would rise. It would slowly flow toward the poles because that's where it's cold, and hot will be attracted to the cold. At the poles, the cold air will actually fall toward the surface and then flow toward the hot air, which again is at the equator. So you would have a cell that would have the hot air flowing toward the poles and cold air flowing toward the equator. Now we're going to really mix things up. We're going to spin the Earth. And when we do that, something amazing happens. The Coriolis effect actually takes that cell and breaks it into smaller parts. So we have high pressure systems, we have polar vortexes, we have equatorial doldrums, and this is what the ancient mariners used to be able to sail from Europe to the New World. They knew that if they went toward the upper latitudes in North America, it would very easily below them in that direction. So in order to get back to Europe, they would have to actually go below the 30th parallel, and where the winds would blow them back to Europe. Every planet in our solar system demonstrates this particular process. Taking a look at our Earth, you can see how the Coriolis effect has broken up the atmosphere into various parts. It's not quite as, it doesn't show it as well here as it would show on a much larger planet like Jupiter. And as you can see, Jupiter fully demonstrates the unbelievable effect of the Coriolis force. So it's definitely a force to be reckoned with. And it's this Coriolis effect, along with the placement of our continents, which gives us our weather, in this case, high pressure going to low pressure, and how these temperature and pressure cells move across not only the United States, but also through Europe and the southern hemispheres. And it also shows how currents over the Earth will move, again, due to the Coriolis effect and the placement of the continents. So you can see where the warm Gulf streams could warm up the United Kingdom, and the cold streams would cool the Atlantic seaboard and also down into South America. The great, shall I say, normalizing material that is on the Earth is something called dihydrogen monoxide, also known as water. Water takes a tremendous amount of energy to heat, and it releases a tremendous amount of energy when it cools. As a result, it's a tremendous normalizing effect on the planet. Water is possibly the one most important thing, not only on the Earth, but also in our solar system and in other solar systems. So next week, we are going to learn the secrets of DMHO, dihydrogen monoxide. And if dihydrogen monoxide can rust these pipes, just imagine what it's doing to your insides. But we'll talk about that next week.